All right, so sample problem G. Okay. I'm going to kind of cue you into this before we get into the problem. This is going to require us to use the quadratic equation and use it as a quadratic. So what I would like to do with this is to take the opportunity to show you how I would like for you to solve this. And of course, when we do anything quadratically related, you have options as to how you can solve it. Okay? I'm going to show you the preferred way as to how we're going to do it in the context of this class. So let's figure out the problem itself and how we know what it is that we'll have to do. So a loaded freight train is traveling with an initial speed of 15 meters per second. The engineer applies the throttle and the train gains speed at a rate of 0.12 meters per second squared. If the train travels a distance of 1,609 meters, which you know is what? 1 mile. Okay. Find the time required to travel this distance graphically using the quadratic position function. Justin, do me a favor. You know what we're trying to solve for. Where are we going to put our happy little question mark? Time. Okay, so that's where our question mark is going to go. We need to be able to solve for time. Hey, Paige, go ahead and give us one thing that we can check into our data table. Absolutely, acceleration 0.12. Okay, Justin, give me something else.
The initial speed was 15 meters.
Okay, good. Initial velocity 15 meters per second. Thank you. Hivash, something else? Good. Okay, 1,609. Do we have any information about V final? No, so we'd have to put our x through that. Now, according to what we've done to this point, we would then use the fact that we don't have V final, we have to use the equation that does not have V final in it. Which, since we know our kinematic equations, is the delta x equals VIT plus 1/2 AT squared. Now, if this were a slightly different problem, we would not have to solve it as a quadratic, meaning this. If our initial velocity was 0, what would happen to the VIT term? It would also become 0. That would effectively drop out. And it would just be delta x equals 1/2 AT squared. Could we solve that algebraically for t? Yeah, we can do that pretty easily. Okay? What if we had an initial velocity and there was no acceleration? What would happen to the 1/2 AT squared term? That would turn into 0, and then we would be able to do the algebra pretty easily to solve for time that way. So the problem arises when we have both an initial velocity, a non-zero initial velocity, and a rate of acceleration, using this equation to solve for time. Because then we have coefficients in front of both of our t terms, we have to go ahead and approach it from a quadratic standpoint. Okay? So here's step 1. Okay? We are going to do the algebra and simply rearrange this so it's in proper quadratic form, which would mean this needs to be a 0 equals equation. So what would we do to bring delta x to the other side? We would subtract it. Okay, what we do to one side, we do to the other. Now I'm going to do a little bit of rearranging because we know the commutative property of addition, 1/2 AT squared plus VIT, and then from bringing the delta x across, minus delta x. Now if you can kind of, for a moment, try to look through the variables that we're using from a physics sense, isn't this just a quadratic? Where we have the 1/2 a is going to produce some number that would sit in front of t squared. Okay, the VI is going to be another coefficient that would sit in front of our t term. Okay, and then we would have the displacement that would be there at the end. Okay? So once we go ahead and plug our values in, we're going to just simply solve a quadratic. Okay? So let's kind of do this together, and the nice thing about this one is we don't need calculators yet. Okay, we can kind of do this together. What would 1/2 of a be? 0.06 t squared. What's our initial velocity? So plus 15t minus 1609. Now, here's the deal. Okay? I know, you should know, the quadratic formula at this point. And we've used it a little bit throughout the course of our year. Most of the beginning of the year we did our math review. That's too slow of a process. Okay? And for a lot of us in here, your math teachers that taught you well, you have the tendency to want to leave things in radical form and do all sorts of crazy stuff. So I want to show you the method that I think is going to work for us effectively and quickly. Once again, like all things in physics, we learn a process and we'll pick up on it. And just like the derivative, we learned how to do that here together. I think most of us that even didn't have calc realized, well, it actually is a pretty easy process once we know what we're doing. Okay, so let's go ahead and let's go to our calculators for a minute. So I'm going to kind of show you up here on the board the things that we are going to do, and we're going to solve this graphically. So for those who know how to do this, hopefully it should be a review from what you've done in your math classes. But before we do that, we're going to do a setup of our calculator's window of the graph. So please go to the window menu. Now, I already have this set up the way that I would like for you to have it set up. We need to change the scale of our graph so we can fit the types of quadratics that we are going to do. So for x min, please change it from the negative 10 that you have, which is the default setting, to negative 100. Please change the x max from 10 to 100. Please change the x scale to 10. Same on our y-axis. Y min negative 100, y max 100, y scale 10. And what this is going to do is going to change, because the default is just set as a 10 by 10 coordinate grid. We are now making it a 100 by 100 coordinate grid. That way we can get a time value for anything that is from 0 to 100 seconds. If we were to have something that were to occur in greater than 100 seconds, we'd have to change the scaling of our graph or take a different approach to it. Okay, so does everyone have our window set? Yes, we all good? Okay, now go to y equals. Okay, I'm going to clear what I had there previously. Okay, but y equals. And what we're going to do is we are going to punch in this function that we have here, our 0.06t squared plus 15t minus 1609, but we're not going to use t. What are we going to use? X, because of how that's set up in terms of our calculator. Okay, so 0.06x, and please use the squared button. Don't do the caret and then 2. Okay, then we had, it was what, plus 15t. Okay, so plus 15x minus, please make sure it's the minus, the subtraction, not the minus sign. 15x minus 1609. And then once you have it, hit graph. Now, we are not going to be able to view the entire quadratic just because of how this quadratic is set up. Okay? But the most important thing is, do we see where it crosses the positive x-axis? Okay. We're going to need to find the point that it crosses over the positive x-axis. Now, just real quick, kind of going back to our notes, I want you to kind of draw what I'm about to put up on the board. And we're going to do this as part of showing our work. So draw yourself a coordinate grid. Okay. Now, because this is a positive rate of acceleration, we're going to see a graph that's going to be concave upwards. So if somehow we could zoom out far enough, that's what we would see, or something to that too. I'm not so worried about this being a scaled drawing of what we have, just a visualization of what we're going to do. Okay, last, we are going to be calculating in our calculator this point. The point where that crosses the positive x-axis. We care not about where it crosses the negative x-axis, because that's before the event even started to happen. We only care about that 1 point. So, in a moment, I'm going to walk you through the steps as to how to calculate the 0. But unfortunately, we have to tell the calculator between what points do we need to calculate that. So it uses terminology called a left bound and a right bound. So what we're going to do is we're going to set our left bound here. And then we're going to go past the point where it crosses the x-axis, and we're going to set the right bound there. So we tell the calculator between those 2 points, calculate where it crosses the x-axis. Are we good so far? Thumbs up, thumbs in between, mostly thumbs up. Okay, good. So here we go. Hit second, calculate. We are going to calculate the 0, which is option number 2. Now, the first thing that should pop up, okay, 1, we see our quadratic function up top, just to make sure that's the right quadratic function. We're good. It asks us left bound question mark, where it says x is 0, y equals negative 1609. Now, it is important to notice that this y starts off as a negative value in this quadratic. I want you to hit enter once. We're going to set the left bound right here, effectively where it crosses over our y-axis. We care about what happens beyond that point. Now, because this starts off as a negative, we need to move the right bound until we cross over the x-axis, which means that we're going to look for, in this case, a positive value here. So the rule of thumb I kind of want you to think of is we're going to move this right bound before we even set it, and we're going to keep going until the sign switches. So right now it's negative 1609. We're going to hit our right button. It's going to be a whole bunch of times because of where we're starting. Don't go too much overboard. Okay, so I'm already negative 800 and change. Keep going. It doesn't necessarily have to be the first point after it crosses over the x-axis where that sign switches. Negative 54 and negative 17. But for me, the first point that I get is 19.925619. Is that what you're getting?
Yeah.
For most of you that are there? It's okay if you go beyond that point as well. We just have to make sure that the sign switches. We went from negative to positive. If we're good with that, we'll set the right bound there by pressing enter once, and then press enter one final time. And what it will do, down here where it says 0, it says x equals, that has solved our quadratic for where it crosses the x-axis. That will tell us the time it takes for that to occur. So how much time does it take our train to accelerate at the rate that we were given for 1 mile? 81.014 seconds. And that would be our response for that. So then we would just go back here. We would say t equals, what would we say it was, 81.014 seconds. So that would be our final response for that. What are you going to show for credit?
Equation.
This. The quadratic, so it's a 0 equals. You don't have to have this piece up top. I just think it's a good point for us to start if you need to kind of think about bringing that across. Okay, so 0 equals. Show us the quadratic with what's plugged in. I do want to see just a very simple diagram so we can see, hey, here's what we're trying to do, and then what our final answer is going to be. So before we kind of march on to other things, I want to give you one more, this pretty simple quadratic to graph and to find this 0. Take that function, please, and calculate the 0.
Yeah.
Most of us kind of getting where we need to be?
Yeah.
Okay.
Isn't that the function of mapping?
Well, we'll see in a little bit. It's not a function for
Why not?
gravity.
Not really.
Negative 9.8 is the rate of acceleration. Okay, so when we solve for this, do we get 6.436 seconds? Okay, most of us should. Now, this one's a little bit more squashed per se, at least along our x-axis, so we can kind of see a little bit more. I know it's kind of hard to see. Is this curve concave up or concave down? Concave down. Negative acceleration graphs are going to be concave down. Positive acceleration graphs are going to be concave up. Okay? So we go ahead and we do that. We start off with a positive value for our left bound. And so it starts at positive. Then we have to go until this y equals becomes negative as the right bound. So we set that. Make sure we go until that sign switches. Okay? Any questions? Now, have most of you done this before in your math classes? I'm not teaching you necessarily anything new, hopefully a refresher. Okay, question? Okay, so then let's just kind of do it together again. We go second, calculate. Okay, then we're going to go to the 0. Now mine's going to be a little goofed because it's already kind of started, so we'll go back to... It'll start you here where we are x of 0, y equals 97. So set your left bound there. And then since y is a positive value, we would keep going to the right until the sign switches. Okay? And then it'll go ahead and calculate that value time again. Good. Yes, ma'am. It is. It's just so close to 0 that it's effectively not. So if you think about what that value is, it's a good question. Why is this y not 0? Go ahead and take that out of scientific notation. That's going to be 0.10 zeros and then a singular 1. Okay, that's going to be so close to 0, let's call it 0. Okay, good question. All right, good.